fine. Okay, so this one, if you read, you will understand. But very important thing is you have to know that how we can choose this T1 and T2. Okay, so this is the best, very important thing you have to know, that to choose switching on time T1 and switching off time T2. Okay, so then normally for such type of arrangement, which means TSCR, so there won't be a harmonic, means it will not generate any harmonic as such. Okay, theoretically it has been said that this form of control does not generate harmonics, whereas TCR generate a harmonics. So now, so when I discuss with other faculty members, so I have learned that harmonics has been not studied as such. Detail of the harmonic has been not studied, so that's why some of your friends yesterday asked what is mean by fifth, seventh, ninth, and then or third order harmonics. Okay, so don't worry about this. So at least I came to learn that you have at least study about the definition of harmonic in the electrical machine or DC or AC. I'm not remembering, but it says that at least basic definition of harmonics is learned. And then what is mean by third, fourth means just you have to know the it is the order of the harmonics. How to eliminate the order of that harmonic, we know that. But basic, so in detail, you have not learned about the harmonics, so that I will not expect you to know all about the harmonics. So if you really want to learn about the harmonics, so final semester, okay, final year, final semester, you can choose a elective. Okay, so based on if you choose a elective related to this module, then you learn in detail. But just now, you have to know the definition of harmonics and then some disadvantages of harmonics and how to eliminate. How to eliminate means not in that detail. Okay, so this more than enough for this module. Okay, okay, so but what we can say is if there is inductive in nature law, so there will be a harmonics. If there is a capacitive, so then there won't be a harmonic. So that's why this switching is not producing or generating any harmonics because it is a capacitive one. This inductance is not functioning as a not functioning as a TSC or a compensation one, but this is just only to prevent the inrush current. Okay, so that's about the TSC basic operation. So now we'll see how we can apply this TSC to control the voltage. Okay, so basic theory of TSC we have learned. Now we'll see how we can control, apply this TSC to control our voltage, which means we are controlling the reactive powers. Okay, so now this figure shows how to implement the TSC. Okay, which will consist, okay, TSC, okay, so it has been said that basic scheme of the TSC consisting of parallel Dell connected TSC elements and controller. So which means actually this is a TSC, and then you know what is a function of L and then all switch. So now this is a controller. Okay, why we need controller? We have to give a command to fire or switch on this thyristor. So that's why we need a controller. If your voltage goes beyond your acceptable range, then this controller will sense what type of controller it is used. We have learned in the control system like PID. Normally nowadays they are using PID, and then they will sense that voltage is going beyond the acceptable range. Then what it will do is it will give a command saying that it is going beyond the acceptable range. Then it will give a command to fire on this thyristor, and then based on that it will control the voltage. So how we will see that this is a basic of this application, how to control. So now let's say when your bus voltage, this bus voltage example, let's keep it at 400 volt. Okay, so just I'm giving example. Okay, so here it has been mentioned in terms of V only. So now 400 volt, and then your reference voltage should be 400 volt, right? It has to be maintained at the 400 volt. So now when your bus voltage deviate from the reference voltage, okay, so actually this 400 is a reference voltage we have to maintain. But when this bus voltage be equal to either increasing or decreasing, Okay, so which means deviate from this reference voltage. Example we have taken is 400 volt beyond the dead band. Okay, so beyond the dead band dB. Okay, so what is mean by dead band? You have to know, right? Dead band means, so at this band, or if it cross beyond this band, then your output will be zero. Means you will not have any outputs. So we don't want such type of a system. Okay, just now you know that what is mean by dead band means. So from name itself, you will know that it is a dead, which means you at this range and then beyond that, so you will not have any outputs. Which means, so if your voltage is uh, crossing beyond this dead band, okay, so your reference voltage is beyond this dead band means actually it is the same as your acceptable range. Okay, beyond the dead band in either direction means either positive or negative. Okay, either positive or negative, which means 400 it may cross 460, down it may come at 350 like this. So if it goes both direction, then control switches, this controller will sense, then it will control the switches. Either it has to put on, switch on this thyristor, or either it has to switch off this thyristor. Okay, based on, okay, or capacitor bank until the voltage return in the dead band, or provided that not all capacitor will be switched out. Okay, so now what it will do is, so now if it cross your reference voltage, I have given example 400. So if your bus voltage goes beyond the, or deviate beyond the reference voltage, then beyond this dead band, then what it will do is this controller will sense this, and then you have to switch on this capacitor or thyristor, which is known as, actually this arrangement is TSC. So this TSC will be switched on, and then it will bring back to the normal voltage. Your bus voltage will bring back to the reference voltage. Okay, so which means 400 volt it will bring back to the, so sometime if you switch on single this TSC, so it will be enough to bring back your voltage within the acceptable range or to the reference voltage. Sometimes single may not be possible, single TSC may not be possible. So then you may have to switch on another TSC, and then it will bring back. Or again, another you have to switch on, and then it will has to bring back. Okay, so based on this, so how much voltage it has been deviated beyond the reference voltage. So this controller will sense, and then it will switch on the TCS. Okay, either one TCS will be enough, or you may have to on second, two, you may have to on third, or so on. Okay, but just now I have said about this so on, which we can arrange this many n numbers of TSC, but we have to see cost wise also. But later on we'll see that. But just now we are talking about how it function. Okay, so this is how this TSC function. Okay, so normally, so now dynamic response. Let's see in terms of dynamic response from the VI characteristic. Okay, so I will take out from the VI characteristic and I will explain how it controls the voltage. Earlier one, just I have explained that theoretically basic concept. So now we drawing the VI characteristic, okay, so of a TSC and the power system. So let's see how it works. Okay, so now this all is mentioned TSC characteristic. Okay, so this side is a capacitive one. Here a little bit of inductive because we have reactor. Okay, so then how it control the voltage. Okay, so let's say this is dotted line is a reference voltage, and then this is a dead band, which means acceptable voltage within this range, which means 400 plus or minus 10% it is acceptable range. Like this we call it as a dead band, and generally this bus voltage will be controlled within the range. It will be given like this. So that's why I'm saying, okay, so this where dV is a dead band, we reference plus or minus d by 2. So normally in most of the equipment you will see that 400 volt like this, and then it will be written plus or minus. So most of time it will be given in terms of percentage, 5% or 10%, which means it is a dead band, right? Acceptable. So it will be governed by this equation. And then, so now how it will control is, so now let's say your system characteristic is this, represent S1, and the S2 is a system characteristics. So now what you can do is, system here means power system characteristic. Okay, so first let's start from S1. When your system characteristic is S1, so now it is deviating from the reference, right? So see here, deviating from reference, and then you will try to switch on the capacitor 1. Here I have written capacitor 1, but actually it is a TSC1. So then what you will do is, so you will get a new operating point at, so initially let's assume that, so initial operating point is at point A, so which is within the acceptable range, like this, means within the dead band only. Okay, are you getting now? So normally you will not get at the end, you will not get a 400 volt exactly. Sending end it might be 400, but when you reach at the receiving end, so either you will have 390 volt or like this, right? So normally this might be in the acceptable range, but theoretically we said that it is 400 volt line, but you will not get that because of drop and all. So now at least, so when your system characteristic S1, so at least you will find an operating point here, even though it is not in the reference one. So you will get that at within the acceptable range. Okay, now let's consider that your system characteristics suddenly change to S2. Okay, so when it changed to S2, so what it happened is, so with switching on this TSC1, so your operating point is here, means it's crossing beyond the dead band. Okay, so now with this, so your voltage deviation is huge one, right? So which means we are not able to maintain at our acceptable range. So now what you have to do is, so you have to switch on another TCR, and then try to bring, if you are able to bring it to reference, then it is more good, more than good enough. But if you're not able to bring to the reference voltage, at least try to bring within the acceptable range. So now if you switch on the TCS2, or means we are switching on the capacitor 2 only, so now you're getting new operating point at C, which is much better, right, than the system 1. Okay, so see here, it's about to be reference voltage. So now this is how we can employ this TSC to control the voltage. Okay, so similarly you try to draw another characteristic like this. If S3 suddenly change like this, you have a huge load and then all. So now if it change like this, so now what it will happen? So now, but switching on 2 and capacitor TSC1 and 2, even if you switch on 2 also, you are not getting within the range. So now what you can see is, so now you have to switch on another capacitor and then bring back to new operating point, let's say D here, and then this will be within the acceptable range. And then keep on, we have to do like this, so on. Okay, so which means this is how we can control the voltage using TSC. So normally when you will inject the reactive power, okay, so actually TSC, okay, TSC means it will not consume the reactive power, but it will inject the reactive power. So see here, so when system 1 is like this, okay, system 1 characteristic, so at least, okay, you have a voltage within acceptable range, at the same time it is at the higher value, right, above the V reference. So now when it changes suddenly to S2, what it happen is, your voltage is becoming low, very low. Why it is becoming low? There is voltage drop. Why there is voltage drop? Because of inductive in nature of the load. So there is more load, right? Which means we have to inject the reactive power so that our voltage will be at the required or within the acceptable range. So that's why we are putting on this. So that's why I have not drawn the system characteristic S1 and then above this one, because this one will be for, instead of TSCR, it will be working for TCR, which means your voltage at the receiving end is getting more than the acceptable range, which means parenting effect may occur and then it is not advisable. So how to reduce that? So you have to employ the T as a TCR, but here I have drawn, that's why I have drawn like the S1 and S2. Okay, so which means when we start with the S1, so it's acceptable range, but if you suddenly, if you change your system character like this, which means your voltage drop is there. Why voltage drop is there? Because there are losses taking place. Losses because of different types of load. Load, when we talk about the load, we are not talking about the capacity one here, right? So normally load are inductive in nature, so your huge drop of voltage will take place. So now in order to compensate that and bring back to our normal voltage range, what you have to do is you have to inject some reactive power. How you will inject the reactive power? By switching on the capacitor. So here I have mentioned capacitor, but it is TS, system is known as TSC. So now that's why, so when it changed to system S2, so your operating point has reached to B if you on C1. Okay, that means TSC1, but it is beyond the acceptable range. So now we have to control that. We have to bring back to the acceptable range. So to bring back to acceptable range, we have to switch on the TSC1 and then it will bring back to the new operating point at C. So we are assuming that it will bring back, and then this is how we'll get within the acceptable range, and this is how we can control. Similarly, you can draw another system characteristic, another, and then we can see that this much capacitance is required to control or inject the reactive power. So this is how it works. Okay. Okay, so this is how it function. The okay, this is the explanation what I have said. Okay, so I have explained already using this diagram, and this is the explanation of our VI characteristic of TSC power system and the power system. Okay, so if you read, you will understand that it is just explanation what I have explained here. Okay, so there's about the how we control the reactive, how we control the voltage. Okay, so okay, that's all about the TSC. Okay, so if you have any doubt, you can ask. Okay, so but this about the TSC, and then so now what we have to do is, since in TSC it will not generate the harmonics, so we will not require to study about the harmonic, how to eliminate the harmonics. But this is a basic how we can control using the TSC. So now till now we have learned about the SVCs. One is TSC, another one is TCR. There are many types of SVC, but these two are most commonly used SVC. So which that's why I have chosen these two, and then but these are all theoretical ones. So now we will not never know when your voltage okay will be low or when voltage drop will be taking place more, and then when we require a TCR, and then when we require a TSC. Okay, so just how I've said, and then where you want to employ that is a question mark. So now what we will do is, after knowing all this theoretical concept of TCR and then TSC, so we will go through the practical SVC system. Okay, which means practically you will have a, when we talk about the static work compensation, practically you will find that combination of TSC and TSC and TCR. Okay, so this is a practical one which we will learn. Okay, so still we have some time, so we'll start next one regarding the uh, practical ST. Okay, practical SVC compensator. Okay, so we will see about the practical compensator. So you have known the individual characteristics. So if you know the individual characteristics, so you combine that two characteristics, so you will get the practical uh, practical VAR compensator or SPC compensator. Okay, so what I have heard is actually this type of device, even though we have not learned, to you it might be a new concept to you all, or for us it is like a new concept, but these types of system are getting obsolete as of now. Getting obsolete, I'm not saying has become obsolete, but it's becoming obsolete because new types of compensation had been started with StackCom, which you will learn in power electronics application. Okay, StackCom will also do this function now, and the UPFC something it has come. Okay, new technology. This to us TSC and a TCR, it's like a new concept, but it is becoming obsolete nowadays. So nowadays it is starting with the StackCom, and then even now latest one it has been started with UPFC. Some okay, so devices has come. So you will learn in the power electronics application. Our syllabus it says how to control the voltage using TSC and TCR. So we will only restrict to this area only. Okay, so with this, so we have uh, completed the TSC and then TCR. Okay, so this is theoretical concept. So now what we have to do is, so with that, so now we have to see the practical VAR, static VAR system, which means it has to be combined there too. Okay, so we'll never know where you have to install the TSC and then TCR. So now if you combine these two and then install in one location, then this will be more convenient. Whenever TCR has to perform, it will perform the function. Whenever TSC has to perform, so it will be performing that function because there is a control system, right? So better, so now it will be better to study about this practical static VAR system or compensators. How you will use this concept for compensating the line network losses. Okay, so now let's see, this is a typical static VAR compensation system. Okay, so this is a practical one. Okay, so in practical one, it will have a combination of TSC as well as TCR. So this first one is TSC and then this one is TCR. Okay, already it has been mentioned. Okay, so this one is TSC and then this one is TCR, and then this one is used for filtering filter, because when we use TCR, so it will generate the harmonic, so we have to filter the harmonic, so we use filter. Okay, so now this is a practical static VAR system. Is actually it is a combination of TSC and then TCR. Okay, so now if you see, observe carefully, if you observe very carefully, you will see that TCR is less, number of TCR employed is less, whereas number of TSC employed is more. See here, example here I have given 3 TSCR and then only 1 TCR. So what could be the reason? So you might be knowing that reason for using less number of TCR and a more number of TSC in a practical static VAR system. This is because, okay, so normally our power system load is inductive in nature, which means most of time we are getting less voltage drop are taking place, right? So which means we have to inject the reactive power. So in such case we require more number of TSC, because reactive power can be injected by TSC, whereas TCR, so most of time I have not heard about this Ferranti effect taking place. Very minimum occurrence is there. So that time only we have to use TCR. So that's why it would be a very minimum requirement. So that's why there will be less number of TCR, but maximum will be TSC, because so most of the load is inductive in nature. So if load is inductive in nature, lot of drop or voltage drop will take place. So which means we have to inject the reactive power and then maintain the voltage at the required or acceptable range. So which means we have to switch on TSC. Okay, so now using this controller, so I'm explaining. Okay, so here if you read yourself, you get that. Okay, so now what you can do is, so based on this controller, if the voltage, okay, bus voltage is going beyond the reference voltage, or what we call is, so now there is a reference voltage, let's keep it as 400 volt, we keep it as 400 volt, and then your bus voltage is actually, it should have 400 volt, right? Theoretically it should be remain same with the reference voltage. Okay, so now let's assume that your voltage has been dropped suddenly to 300 volt. Okay, 100 drop, voltage drop is taking place, right? So now in such case, this potential transformer will be sense this, and then what you can do is, so this controller will sense that your voltage, bus voltage is going beyond, or the voltage drop is huge there, 300 volt, or going beyond your reference voltage. So now based on that, so this will command to your TCSR to switch on, so that it will be bring back to reference voltage or 400 voltage. So now your controller will sense that, and then controller will command that to on TCR. Okay, so this TCR will bring back to the reference voltage, or you may have to on another TCR to bring back, depending upon the magnitude of your voltage drop. So it will bring back. Okay, so it's like this. And then let's assume that your Faraday effect is taking place like 600 volt, it has been crossed. Means your bus voltage is going beyond the reference voltage. So in such case, what you have to do is, this controller will sense your voltage is going beyond the reference voltage 600 volt, our reference voltage is 400, and then it will command this TCR to switch on. So which means it will observe the reactive power, and then it will try to maintain back to 400 volt. So this is how practical system will be there. Okay, earlier one we have learned only about the separately about TCR and then TCS. So if you combine these two characteristics, then you will get practical static var system or static var compensators. Okay, so this is how we can do it. But now how we will choose requires, okay, of this practical application. So the required speed of response, whether you want slow response or fast response, size ranges and flexibility, losses and costs are among the important consideration in selecting the configuration for any particular application. So for any application, if it is for 400 kV transmission line, so what you have to do is, so what type of speed response you require. So you have to see that, then size ranges, flexibility, how we can use that, losses, how, what are the losses taking place in this transmission line, then cost. So definitely if we increase the number of this TSC or SPCs, cost will also increase. So we have to optimize. So based on that, so we will select for any type of particular applications. Okay, so there, here I have just given an example for, okay, practical as static bar system. Okay, so this consists of a TCR, TSC, and then Harmonic filters, which we can eliminate or filter out the harmonics. Because of this TCR, there will be a harmonic generation in the system, so that harmonic has to be removed, so we have to use this filter. Okay, so this is about the practical SVR. So now you can see that, so you just combine these two practical VI characteristic of these two, TCR and then TSC, then you will get the practical one. Okay, so but what you can see is, so here there is one advantages is, so for this TCR, okay, so it said that filter are capacitive and then produce reactive power. So because of the employing of TCR, so you have to have a filter. So filter normally it will have a capacitor. So when there is a capacitor as a filter, so this capacitor will also produce the reactive power. So how much it will produce is, it says that 10 to 30% of TCR rate, MBR rating. Means So if your rating of TCR, terrestrial control reactor, is, let's say, 30 mega MVAR, so now it will generate 10 to 30% of this. Means it is advantageous, right? One way it is advantageous. So when we are trying to filter out the harmonics, you are also producing a reactive power, which means it will reduce the number of TSC in the systems. At least it will generate 10 to 30% of this. Okay, so now based on this, so what you have to do is, so now we just see the VI characteristic and then VQ characteristic, which means voltage reactive power characteristic and voltage current characteristic. So steady state, this VI characteristic of SPC is shown in this figure 2A, and then VQ characteristic for a practical for system shown in figure B. Okay, so normally, so what we have seen is, we have seen there is a slope. Okay, and then here also we have a slope. So we have combined these two, and then normally this range, in this slope range, is called it as a linear control range. Okay, this is linear control range lies within the limited determined by the maximum susceptance. Okay, so normally you can find the reactive power VQ is equal to, actually it is same as our power on VI, right? And then P equal to VI, so then you can write in terms of VI. So now I will be equal to V by R, so which means you will get V square by R. So reciprocal of resistance is known as susceptance, so that's why you will find this B. Okay, instead of V square by R, it has been written BC by V square. BC is a susceptance of the capacitor. Similarly here you will get this. Okay, so this is just a combination of two SPCs, that is TCR and then TSC. Okay, so if you see this, then when you know, if you know the characteristic of this TCR and TSC, then you will know this the characteristic of the practical static work system. Okay, this is about the practical SPR. So you can just read here. So same I have explained with this diagram how it control PI. Okay, so the voltage. Okay, so it's explaining about this one. Okay, so now very important thing is, another important part is application of static work compensation. So where you will use this static work compensation? Actually, we are talking about the practical static work compensation. So control of over voltages, temporary over voltages. Okay, so we can control the over voltages taking place by employing TCR. Then prevention of voltage collapse, which means voltage sometimes it may become zero. So if voltage becomes zero, so you will not get the active power. You have to know that, because active power P equal to VI. Okay, for single phase P equal to VI cos phi. So now if voltage has become zero, so now you will not get the active power. So now how you have to bring back the voltage to the required one? You have to inject the reactive power. So how you will inject the reactive power? So you use TSC. So that is prevention of voltage collapse. Then enhancement of transient stability. Okay, so what we have to do is, so when there problem, you might have studied in the stability in the last semester. So there is a different types of stability: steady state stability and transient stability. So if you employ static work compensation, then transient stability will be improved. Then damping of system oscillation will also be improved. So generally these four applications are there, but at the same time in sub-transmission and distribution system, also this SPC are employed, not only in the transmission system, even in the sub-transmission and distribution system level, SPC are used for balancing the three phases of system supplying unbalanced load. So normally we may have to supply the unbalanced load. In such case, if you use a SPC, then it will be balancing the three phases. Okay, so they are also used, another type of use is to minimize the fluctuation in supply voltage. So normally we used to get a fluctuation in voltage, which means these SPCs are not used. So SPCs can be used for minimizing. We cannot say that we will completely stop the fluctuation, but as far as possible, so it will minimize the fluctuation in supply voltage. Because why supply voltage is fluctuating, you know that because of different types of load. Okay, so these are the different application of the static bar system. Okay, so in the practical static bar system, so only thing you have to know is there will be a combination of TCR and TSC. How it function? If it is under voltages, so it has to perform that. Because why under voltage is taking place, you know that there is a huge load. Okay, so load consume the reactive power. Okay, so which means we have to inject the reactive powers. How we will inject the reactive power is by employing TSC, and if there is over voltages, TCR will perform. Okay, so practical static bar system is combination of TCR and TSC. Okay, so with this, so we are completing about the SPCs. Okay, so with this we are completing about the SPC, and then you have to know that in power electronics application, you will learn that this SPC is almost becoming like a obsolete now, becoming obsolete because that new technology like stack comms, and then now again another type of technology is coming now, UPFC something. Okay, so this is overtaking the our SPCs like TCR and TSC. So next lecture in power electronics application, definitely sir will be teaching on stack how to control the voltage and all. But in our case, so we are limited to TCR and TSC. Okay, so that's all from my side for today. So if you have any doubt, so you can ask, or if you don't have doubt, so we will stop here for today's. Okay. Okay, so thank you for coming online, and then
Thank you, sir.
okay,
Thank
so
you, sir.
hope all of you are staying safe and then not roaming after 7 p.m., right?
Yes, sir.
Okay, so
No, sir. At home only, sir.
okay, so stay safe, and then let's pray to meet soon. Okay.
Okay,
Okay,
sir.
sir.
Okay, so
Bye,
thank you for
sir. Thank you,
coming.
sir.
Thank
Yes,
you. Bye
sir.
bye, sir.
Okay.